Good afternoon, everyone. I hope you're having a good day so far. Today we're going to focus primarily on the material from sections 15.5 and 15.6 of the textbook, which is the rest of the material that you need for this week's homework. Remember that you can pause me at any point in time along the way to ask me questions, and you can do so either in the chat or using your microphone. My computer audio is on this time around, so you should hopefully be able to reach me over the microphone if you need to. So the first thing we're going to talk about today is intensity. Now you've probably heard light being described as intense before, but it's not just light waves that have an intensity to them, so sound waves also do. So intensity is given by the equation I is equal to power divided by area. So this I here is our intensity. Power is our P, and then A is our surface area. And so if you're thinking about the surface area, it's basically what area is our wave coming into contact with. So if we have a focused laser beam of light coming through and hitting a wall, the area in particular is going to be the place where the beam meets the wall. So if we looked at what's happening in the wall's perspective, and we kind of zoom in on it, our laser beam would be hitting in a roughly circular area. So it's going to look something like this. So the area in red here, this would be your area that you would use in the equation. So if you knew the power of the laser beam and you knew the area of that circle, then you'd be able to calculate the intensity. So are there any questions so far? Alright, so sound and light travel in waves, and a lot of times, so a laser beam is a very focused type of light, very concentrated, but if you just like if you stomp your foot on the floor, the sound originates at one specific point, and it kind of travels radially outward in spherical waves. So if we think about how a lot of waves travel, it would be spherical. So we have kind of like a source for our wave, which I'm going to draw with a little dot, so that's where our wave originates from. And then it moves spherically outward. So would have, it's on the whiteboard, I can only draw it in 2D, so they're going to look like circles, but remember that these are actually spheres. So we have, at one distance our wave will look like this, at the next distance our wave will look like this. So this one has a radius R1, this one has a radius R2. And so the thing about our wave is that if we have a constant power source, the power is going to be the same at every point. So whether we're here or somewhere else, the power will be the same. The thing that changes is the area, and since the area is changing, that's going to change our intensity as well. So if we wanted to compare the intensity at these two different points, we can just write out our equations. So I'm going to call I1 the intensity corresponding to R1. So we're going to have I1 is equal to power divided by the area of that, and we'll talk about what that area is in a second. And then off to the side, I'm also going to do the same thing for I2. So we're going to have I2 is equal to the power divided by our area 2. Now the surface area of a sphere is 4 pi r squared. So since these are spherical and not circular, we have to use 4 pi r squared. So we're going to have I1 is equal to power divided by 4 pi r1 squared. And then for I2, we're going to have the same thing, power divided by 4 pi r2 squared. Now, what I'm going to do next is I'm going to solve out for power in both of these and then set them equal to each other. And the reason why this is helpful is you may not know what the power of your light source is, or your source is, whether it's be light or sound or whatever. And so you can find a way to figure out the intensity at different radii using this relationship without power. So if we go ahead and solve out for power, we're going to have power is equal to 4 pi r1 squared I1. And we're also going to find that power is equal to 4 pi r2 squared I2. And since we have the same p here and the same p here, we can set these two terms equal to each other. So we're going to have 4 pi r1 squared is equal to, or times I1, is equal to 4 pi r2 squared times I2. So from here, there's 4 pi on both sides of our equation, so we can cancel the 4 pi. And we're going to get that I1 r1 squared equals I2 r2 squared. So again, this relationship is useful if you don't know what the power of your source is and you want to find information about the intensity at different distances away. So are there any questions so far? All right, so the next topic we're going to touch on is energy. So the book in this section on intensity talks a little bit about energy, but they don't really frame anything in terms of equations. So I think it's helpful to think about what they're saying in terms of equations. So if we go back to the idea of power, we know that power has units of watts. And so, again, I'm going to use these brackets to denote units. So the units of power are watts. Well, what's a watt? A joule per second. So this is joules per second. And so, as this kind of hints at, our power is our energy per time. So if we have a constant power source, we can say that our power is equal to our change in energy over our change in time. And if we then want to figure out what our energy is, we could just go ahead and multiply both sides by delta T, and we're going to get that our energy is equal to our power times our time. So are there any questions on this part? All right, so the next thing we're going to do is we're going to move into an example. And this one will touch on both ideas relating to intensity and energy. So let's suppose that Cupcake the kitten is perched on your shoulder, and she meows. The intensity of her meow is I equals 3.16 times 10 to the minus 8 watts per meter squared. And so she's sitting on your shoulder just a few inches from your ear. The radius of your inner ear is about 0.0042 meters. And so the first thing we want to know is how much power is delivered to your eardrum. So if we go back to our power equation, or our intensity equation, we know I is equal to power divided by area. So if it's the power that we're looking for, we're just going to go ahead and multiply both sides by the area. So we're going to have power is equal to intensity times the area. Now you already know what our intensity is, but what would be the area of your inner ear surface? Well, we're going to treat it as though it's roughly circular. It's not perfectly circular, and of course it's going to vary from one person to the next. It's always kind of like an average estimate, but it's roughly circular. So we're going to use our old friend pi r squared here for our area. So our power is equal to I times pi r squared. And then from here it's just a matter of plugging in our variables. So we're going to have 3.16 times 10 to the minus 8 watts per meter squared times pi, and then our radius is 0.0042 meters quantity squared. So we plug this into our calculator, and we get that P is equal to 1.75 times 10 to the minus 12 watts. And if we look at our sig figs, this one only has 2 sig figs, so we're going to go ahead and round this to 2 sig figs. So this is the same thing as 1.8 times 10 to the minus 12 watts. Are there any questions on this first part of the problem? All right, so the next thing we're going to want to look at is the energy. So if Cupcake's meow lasts for half a second, how much energy is delivered to your eardrum? So part B, we want to know the energy. And we're given that our time is half a second. So if we just go back to the energy equation we had a moment before, we have our energy is equal to our power times our time. And then our power from part A was 1.75 times 10 to the minus 12 watts. And we're going to multiply that by 0.50 seconds. And that will work out to be 8.76 times 10 to the minus 13. And our units are going to be joules. So watt is a joule per second. We're multiplying this by seconds, so we're going to get units of joules here. Now the last thing we have to consider is sig figs. This one only has 2. So this is going to be, our final answer will be, our energy is equal to 8.8 times 10 to the minus 13 joules. So are there any questions on this problem? All right. If we have no further questions, then we're going to move on to the next topic, which is loudness. And this is also called sound intensity. So loudness is basically a way of ranking how intense sounds are. And so In the last problem, I gave you cupcakes meow in units of watts per meter squared, but a lot of times when we're talking about sound, it's more convenient to talk about it in decibels. And decibels are the units for loudness. So loudness is kind of like just like a unit conversion, but there's also a log thing involved, so it's a little bit trickier, but you can just think about it, it's the same type of thing as intensity, it's just another way of measuring it on a slightly different scale. So our loudness is given by the equation. We use the Greek letter beta for loudness. And that is equal to 10 decibels times log base 10 of I over I naught. So I is our intensity. And I naught is a constant that's referred to as the threshold for hearing. So I naught is equal to 1.0 times 10 to the minus 12 watts per meter squared. And this is the sound intensity that is needed for the average person to hear something. So it's kind of the cutoff point for the average person. And of course, everyone is different, so the actual threshold for you may be different, but we use I naught as a convenient metric, so kind of the cutoff point beyond which people can't hear anything. So are there any questions so far? All right, so let's go into an example then. So Molly the puppy is standing half a meter away from you. So we have our radius is 0.50 meters. And she barks, and her bark is about 50 decibels. How loud would her bark be if she was standing 15 meters away from you? So we want to know how loud would her bark be 15 meters away. Well, if you look at the equation for loudness, there isn't radius in there anywhere. So the tricky thing about loudness is that a lot of times you may have to convert into intensity and then convert back if the information you're given is distance instead of the intensity. So what we're going to have to do is we're going to take our loudness equation, we're going to rearrange it to solve for intensity, and then we're going to have to take that intensity to figure out the new intensity and then convert back. So it's a little bit of an involved process. So our loudness equation is beta is equal to 10 decibels times log base 10 of I over I naught. So the first thing we're going to do is divide both sides by 10. And so we're going to get log base 10 of I over I naught is equal to beta over 10 decibels. Now, getting rid of the log is kind of the tricky part if you haven't done algebra in a little while. So since this is log base 10, if we take 10 and raise it to both sides of the equation, then we're going to be able to get rid of the log base 10 on this side. So this side is going to become I over I naught, and this side is going to become 10 to the beta over 10 decibels. And I'm going to drop the decibels for right now, but remember that this one has units of decibels. So that's what our equation is going to look like now. And so then the last thing we're going to have to do is we're going to have to go ahead and multiply both sides by I naught, and then we'll be able to figure out what I is. So we're going to have I is equal to I naught, and then times 10 to the beta over 10. And so from here, it's a matter of plugging in our values. We have I is equal to 1 times 10 to the minus 12 watts per meter squared. And then times 10, and then beta is 50 decibels divided by 10 decibels. And so if we plug this number into our calculator, we're going to get that I is equal to about 1.00 times 10 to the minus 7 watts per meters squared. And I'm going to call this one I1 because it's the intensity at what we call radius 1. So are there any questions to this point? All right, so now that we have our first intensity, we have to figure out what our second intensity is. And this is where we're going to go to our relationship we found earlier. The I1 R1 squared is equal to I2 R2 squared. We want to know what I2 is, so we're going to divide both sides by R2. So we're going to have I2 is equal to I1 times R1 squared over R2 squared. Now I1 we found was 1 times 10 to the minus 7 watts per meter squared. And then R1 was 0.50 meters. And we're going to square that. And then R2 is 15 meters. And we're going to square that as well. And we're going to plug this number to our calculator. And so we get that I2 is equal to 6.67 times 10 to the minus 9 watts per meter squared. So that's our new intensity at our new distance. So are there any questions to this point? All right, so the last thing we have to do is take this intensity we just found and plug it back into our loudness equation, and then we'll know how loud her bark is at 15 meters away. So our loudness equation is beta is equal to 10 decibels, and then log base 10 of I over I naught. So we just have to plug in our value for I and I naught, and so this is going to be 10 decibels log base 10, and our new I we found was 6.67 times 10 to the minus 9 watts per meter squared. And then I naught is 1.0 times 10 to the minus 12 watts per meter squared. Plug this number into our calculator and we get that beta is equal to 38.24 decibels. And now we take a look at our sig figs. We only have 2 down here, so this is going to be equal to 38 decibels. So are there any questions on this problem? Alright, so the last thing I have planned for you, we're going to hop back to section 15.2 for a second and introduce the equation that we need for the new question 2 on this week's homework. So originally, I did not go over this equation because it's more of a chemistry thing, and it's not one we use a lot in this class, and you didn't have any homework problems on it. But now that you do, it's important to touch on. So this one's about the speed of sound in an ideal gas. And it's given by the equation, the speed of sound, so we're going to use V sub s to denote that. And that's equal to square root of gamma RT over M. So there's a lot of constants here, and we'll work through what they are. So gamma is a constant, and it depends on what type of gas you have. So gamma is equal to 1.67 for a monatomic gas. And it's slightly different for a diatomic gas and so on and so forth. But this is, and the book has other numbers. I know they have at least a diatomic gas in there as well. But for a monatomic gas, it's 1.67. R is called the gas constant, and it's equal to 8.3145, and it's joules per mole Kelvin. And so then this T here is our temperature. And it has to be in Kelvin to get the right units. And then M here is our molar mass. So are there any questions on this? Alright, so that's all the new material I have for you. Do you have any questions on the homework or on anything that we covered today? Alright, well, if you end up having any questions, don't hesitate to email me. I can help you with homework by email if you need it. And if you have no further questions, then have a great day.